Greetings, and so we come to the end of our, what is this? Now I've got to check and see where we're at in lectures. I've lost track of time. We're at the end of our fourth week of online lectures. I believe that's correct. Let me check and make sure. 1 week, 2 weeks, 3 weeks. Yeah, we're at the end of the fourth week of online lectures. So today's lecture and then the next couple of lectures are going to be on topics that you should know exist, but, and I always hate saying this, but you aren't going to be held responsible for, or for which you will not be held responsible. You're not going to see this on your final examination, and you're not going to see this in a programming assignment, but you will see this down the road. Doesn't matter what your major is, doesn't matter what your field is. You will see these topics again, okay? And so for the next 3 days, or the next 3 lectures, this will be sort of foundational work for continuing forward writing code and designing solutions, algorithmic solutions. If you're going on to CSI 201, which many of you are, then you will see these topics again, and you will have to use them in CSI 201. So this is a bit of what in literature we call foreshadowing. So with that said, I'm going to drop the video link and start with some with some PowerPoint slides. I should not try and talk and drink at the same time. So here's our PowerPoint slides. Oh, come on. There we go. So the first topic that I'm going to cover is called recursion. And recursion is a pretty simple idea, but it's a little hard to wrap your brain around. This is the fundamental idea behind the design of the programming language Lisp. So in Lisp, you can write while loops and you can write for loops, but that's not the way Lisp was designed to work. Lisp was designed to work using recursion. And so it's naturally recursive. And that ties itself to mathematics a little more closely. So a recursive function is quite simply a function that calls itself. Well, wait a second. If I call cosine, cosine doesn't call cosine. So there are these recursive ideas that come from mathematics, and that is that data is passed in the function parameter and then is changed. And that change data is passed to another call of the same function. And so what happens is you chain up these calls to functions. And then when you finally hit a stopping condition, a condition that says you're done, we've got the answer, then it halts the recursion and it forces the function to return. And then it returns and returns and returns all the way back to the calling person. Now there are some very important algorithms in the world that are recursive, naturally recursive. The fastest sorting algorithm for large amounts of data is quicksort, and quicksort is naturally recursive. In fact, quicksort is really hideous to implement iteratively. You want a programming challenge, write quicksort iteratively. In fact, that was a programming assignment in my graduate algorithms course at the University of Michigan. Here, write quicksort iteratively. And when we started out, it was like, holy crap, this is hard, this is nasty. I had written the recursive version of quicksort, and it's quite easy. It falls out quite naturally. So that's why we look at recursion. There are many algorithms that are naturally recursive. Okay. Now, in mathematics, we often will talk about these as recurrence relations. So notice that the recur is the root word here, recurrence, recursion. So a lot of those mathematical ideas are based on recursion. The ideas or the algorithms are written as a recurrence relation. Now, these make programming the recursive function much easier because they're really just a roadmap for the algorithm. They show you the stopping conditions and the recursive conditions. That is, the conditions of the data under which you will call the function again, and the conditions of the data under which you will return the answer, or that the answer has been found. Okay? So here's a factorial recurrence. This is really stupid recursion. It's easy to write as a for loop, but it illustrates the idea quite nicely. That is, the factorial of n is equal to n if n is equal to 1. So the factorial of 1 is 1. Makes sense, right? The factorial of 2 is 2 times the factorial of 1. So that's the second part. That's the otherwise part. And you notice how we have an if and an else. It's quite simple, quite straightforward. If n is equal to 1, then we have the answer. We return n. If n is not equal to 1, then we multiply n by whatever gets returned from calling factorial, but passing in n minus 1. So we've simplified that data, and now we've made a recursive call. And eventually, because we keep subtracting 1 each time, that n will get down to 1. Okay? Now, that's not an interesting algorithm. Here's our first interesting algorithm. And this is Euclid's greatest common divisor. It's a very simple idea that can be implemented either iteratively, that is using the loop, or recursively, that is a function calling itself. So I don't have the recurrence relation here for Euclid's GCD. What I've got is a pseudocode of the algorithm. Now, everything is an integer. There are no fractions here. There are no real numbers. And the definition is quite simply, if you want the greatest common divisor between A and B, if B is 0, A is the answer. Else, the greatest common divisor is calling the GCD. Let me fix that typo. Well, it's not a typo, just a miscapitalization. Slideshow from the current slide. Okay, so if B is equal to 0, then A is returned as the answer. Else, the answer that gets returned is calling GCD again, putting B as the first parameter, and A modulo B is the second parameter. So notice that A and B came in. A was the first, B was the second. And now we're saying B is now the first and A modulo B is the second. Well, A modulo B is guaranteed to be B or less. That's the way modulo works, right? It's the remainder. Now the recursion is in the else, and the stopping condition is in the if. Okay. So we're gonna keep recursing until we hit that stop condition, and we are guaranteed to hit that stop condition. Now there's a mathematical proof that we're guaranteed to hit that stopping condition, but we're not going to look at that proof, that mathematical proof here. Now, notice the recursive properties. All recursive algorithms have the following. They have at least one stopping condition. If you don't have a stopping condition, then you get infinite recursion. Infinite recursion is exactly the same effect as an infinite loop. It'll just crash your program faster. An infinite loop, I can write you an infinite loop that'll run forever. I cannot write you infinite recursion easily that will run forever. And the reason is that each one of those calls, those recursive calls, are taking up some memory and they're taking up some resources. And so when you string all those calls down infinitely deep, you're going to run out of resources and it's going to crash your program. So, and if I've got enough time at the end of this lecture, I'll show you a program that'll crash, okay? So there's one or more stopping conditions, and those return the answer. Sometimes we call these the base case or the base condition. There are also one or more recursive calls where the data passed into the function is simplified or transformed or altered in some way. And then the recursive call is made, calling the function itself. So the function is calling itself using this newly simplified or transformed data. Okay. Now I'm not Russian. Matryoshka, I believe is the way you say this. So a Matryoshka example. I'm going to go back in. I'm going to drop the share for now and turn video back on. Okay. For those of you who know what that is, this is a Matryoshka. It's a nesting doll, okay? And this is a really good analogy for recursion. The data, think of the data as the image that's been painted on the doll. So here we have Father Christmas, okay? Very nice, you know, package. Now, if this were a recursive function, okay, the data is what's painted on here. So what a recursive function would do is say, have we reached the end yet? Well, no, we haven't because there's a scene here, okay? So we can simplify this. And so we change the data inside of the call to the function. We get the call to the function, and then we change the data. And we call the function again, okay? This looks similar to the data we had just before, okay? And in fact, there's even a present right there, but the present is different. It's not quite the same. In fact, before, the present was in a bag. So we've taken the data, we've simplified it, and now we have Mrs. Claus. Is this the end condition? Well, it turns out, no, it is not. That is not our base case. So the function simplifies the data and calls again with new data. Okay. The new data still has a hat, but the hat has changed. The data has changed, okay? In this case, now we've got a snowman. Maybe this is Frosty, I don't know. So the snowman, okay, has a gift, but the gift is an apple, okay? Interesting. So the data is changing. It's getting simpler, okay? What's being, painted on here is simpler, but we're still not at the base case yet. And so we're going to call this function again. The function works the same way each time. You notice how the function always works the same way. Like I open it up and there's the next call, okay? So I open it up and there's the next call. This call is just a tree. Very simple. The data has gotten much simpler. Remember where we started, right? We started up here. And in fact, if I had a shelf, what I would show you is there's a call here, okay? And then there's a call here, okay? And that call is still hanging. We haven't returned from these calls yet. They're still waiting for the solution. And then there's another call here, and it called this. So we're 4 calls deep already. We had a call to Santa, we had a call to Mrs. Claus, we had a call to the snowman, and we have a call on the tree. Still not the base case. And so we make another call. And so this call goes down to here, okay? And this is the base case. It is as simple as we can get. It is a gift from the looks of it, but we can't go any further. We've hit the base case. So this is going to get returned. And as it returns each level up the call tree, okay? Now I want to make sure I get these put together correctly so the images all line up properly. So there's, it returns. And so this return value though, what's inside is actually getting passed all the way back out. So when this one returns, it comes back up to this one, but it actually doesn't, let me get this put back together correctly. But this one doesn't use the data that was here originally. It's going to pass this back up again. So this gets passed back up again. It gets passed up to the snowman level. And the snowman level is like, oh, we just got a return from that recursive call. I'm done, but my data doesn't matter anymore. I found the answer. And so I'm going to turn and in turn return the answer up. Now the answer comes up to, and let's see, to this level. And this level, again, says, I got the data back, I got the return value back, but that return value, this is the answer. And so I'm going to take this and pass it back up. It goes back up to this level, okay? This level says, okay, says, I'm done. The recursive call came back, I'm done, and I'm going to pass the answer up to whoever called me. And so the answer comes all the way back out, and I go, ah, here's the answer. Okay? Now, that's a lot of work. But for many recursive algorithms, the recursion is simpler than the iteration, like I mentioned quicksort before. So I'm going to drop our video again, and I'm going to share out the remaining slides that I have. Okay, so that was our I can't say it, nesting doll example. Okay, so the next thing I want to do is show you some examples of these recursive algorithms. Very little code goes into these. It's how the code works that makes it hard for you to understand or hard for it to wrap your head around, okay? So we're going to start with factorial. Factorial is really easy to do, really straightforward. I can compare it to the iterative function, and you know, that's going to work well. Euclid's GCD is a good example of a problem where the number of recursive calls isn't known. I can tell you, when you pass in a number into recursive factorial, like 12, you're going to chain 12 deep recursive calls until you hit that base case. And then it's going to pop all the way back up. It's going to return all the way back up, okay? For Euclid's GCD, you pass in 2 numbers, and I cannot guarantee you how many calls there are going to be. Now, I can calculate it, but sometimes calculating it in and of itself is solving the GCD problem. So Euclid's GCD is a really elegant little algorithm, and it's naturally recursive, okay? And then we're going to look at Fibonacci, and in particular, what is the nth Fibonacci number? So whatever n is, what's the 100th Fibonacci number? And you will not be able to calculate the 100th Fibonacci number this way, because Fibonacci is an absolutely horrible recursive algorithm. And what this is, you know, why I'm using this as an example is to show you that recursion is a tool, and it's not always the best approach. for a given problem. Recursion's an excellent approach to sorting things quickly. It's an absolutely horrible approach to calculating factorial. So with all of that said, I'm going to drop the share, and I'm going to start up a Cygwin terminal. So this is just locally programming these examples. Okay. And here's the screen I want to share. Okay. So off onto my flash drive, into courses, course common, CSI 21, COVID lectures, oh, that's all the further I want to go because I want to make directory. And this is lecture 19. There we go. So the first one I said I was going to do was factorial. So I'm just going to call this one factorial.cpp. Pretty simple, pretty straightforward. Okay. Pound include IOStream using namespace std. Okay. I'm going to take off the auto indenting. Set null c indent. Okay. And now I need that recursive function. And in fact, I'm going to write two functions. One's recursive, one's iterative, so you can see how different the code looks for those two. So I'm going to call it refact for recursive factorial, and it's going to take a single parameter n. Okay. And then I'm going to write it just like we had in the recurrence relation. So that's it. If n equals 1, return n. Then in the else, it said, well, otherwise, so that's the else, otherwise, we need to return n times the refact of n minus 1. Okay, so we've taken the data and simplified it. We've subtracted 1 from the original number coming in. We've passed it into the recursive call. And then when that returns, we're going to multiply it by n. So if n came in as 11, it's not equal to 1. So we're going to return 11 times refact of 10. And refact of 10 will come in, 10 will come in. So this is a new call, a new instance of this function. And it'll say, am I 1? No. Okay, so I need to return 10 times refact 9. And so this is going to go down, 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 down until we get to 1. And then it will start returning. Okay. That's it. That's all of the code entirely. Pretty simple stuff. Now, I forgot to give refact type. So I need to make sure that that's an int. And now I'm going to go down and write int itFact. So this is the iterative version of factorial. It too takes integer n as a parameter. Okay. And I'm going to need a couple of local variables, one called fact and one called int. I probably should initialize fact to 1. I don't need to initialize because I'm going to say for I equals n, I greater than 1, I plus plus, oops, I minus minus. I'm going backwards in the loop, right? Fact equals fact times I. Return fact. Okay. So that's the iterative version of factorial. And notice that that code is a bit more complex. It's got a couple of local variables, but there's no calls to any other functions here. So recursive factorial, iterative factorial. And now I'm going to write a main that will simply say, so there's a prompt for our input. I'm going to cin the num. Okay. I'm going to range check this. So you should get into the habit of putting in error checking now. We're sophisticated enough programmers. The error checking should come out immediately. So cout and there's why I put you on a 70 column limit. You see how that wraps and makes the code look horrible on the screen? That is entirely why. So if I were to go back up and split this, like that, see how it's easier to read. Looks better. Okay. I also need to exit at this point. So and exit might require the C standard library. So I'm going to include that up here. CSTDLIB. Okay. Oops, forgot my opening quote there. Okay, so the first one, I'm going to call RE fact on the num. The second one I'm going to call it fact on the num. Okay. And we're going to see if indeed these two come up with the same answer. If they don't, then I know I've got something wrong in my code. Let's compile that and see if it runs. So I'm going to have a lot of executables in here, and I want to name them after each piece of code. So this one's going to be named factorial. Whoops, /factorial. And now my virus scanner has to say, yes, yes, this is safe. There's no virus in this executable. So I'm going to do a little bit of error checking first. So that should give me an error, which it does. Zero should give me an error because you can't calculate factorial on zero. One should give me one, and they both do. So if we were doing a mathematical proof, this would be called induction. Show that it works for the first step, then assume it works for the n minus first step and try n. Well, we aren't doing mathematical induction. So I'm going to do a factorial that I can calculate in my head. So the factorial of 5 is 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1, which is 120. So if I say factorial of 5, I should get 120. And look, both of them gave me 120. Interesting. Okay. Now, I'm going to go back in and edit this stuff. Okay. And so for now, what I want to do is just put a print statement at the top of each of these functions. Okay, so in the first one, I'm going to say refact called with. Okay. And then right here, need my quotes again. Ugh, this stupid virus check software. Okay, I think I've gotten rid of that. It was just annoying the hell out of me. So I was right up here. Refact, returning n times refact. Actually, let's put the numbers in there. And so that's going to give us a visual indication of how deep this recursion goes. Okay. I'm going to do something similar up here in itfact. And then we'll see that itfact only gets called once. Okay, so let's get out of here. Let's recompile. What line is that? Line 20. Go to line 20. Oh, I just completely messed that up. I must have deleted something that I shouldn't have. Okay. So let's do that 5 again. And we can see the number of calls that we're going to go down. As soon as my virus scanner is done, 5. Well, actually, let's do 1. I'm going to do 1 first. So refact called with 1, refact returning n, recursive factorial says 1. Itfact called with 1, iterative factorial says n. So actually, in itfact, okay, so that's just going to keep those two things working very similar. So there we go. I asked for the factorial of 1. Refact is called with a 1, and then it returns n, which happens to be 1. And so recursive factorial says 1. Itfact is called with 1, and itfact is returning the value in fact, and that value in fact is 1. Let's do this again. And now with 5. Look at all the calls to the recursive functions, okay? So refact, the recursive factorial, is called with 5. So now refact is going to I misspelled refact. Refact is going to return 5 times refact of 4. Well, that second call is called with 4. And so refact is going to return 4 times refact of 3. Refact of 3 is called, okay? And then refact is going to return 3 times refact of 2. So we call refact with 2. Refact is going to return 2 times refact of 1. Refact is called with 1, and it returns n, which is the 1, which then replaces, so it's coming back up. So it's right here, it's coming back up. So this whole piece gets replaced with 1 times 2, which is 2, returns. So this becomes 2 times 3, which returns, that's 6. So this becomes 6 times 4, which is, what is 6 times 4? 24, okay? And that returns. 24 gets right here, that's what got returned, times 5, and that's 120. And then this returns, and you get the 120 back out right there. Itfact, the iterative version, just gets called once, and it calculates it and returns it, no problem, okay? So there's a good look at how factorial works, both iteratively and recursively. The next one we're going to do is Euclid's greatest common divisor. So Euclid.cpp. Okay. Now, set no C indent. I definitely need to include IOStream here. Using namespace std. I misspelled IOStream. And I'm probably going to use exit in here, so I probably should get the C standard library as well. C standard lib. Oh, my fingers were one off on the keyboard. Ah, how annoying. Okay, so now we need that Euclid's greatest common divisor function. It too is going to be an int. I'm going to call this Euclid GCD, and it's going to take an int A and an int B, 2 parameters. Okay. Now remember our base case, right? If B is equal to 0, okay, I'm going to stop using the curly braces on single lines of code because a single line of code counts as a block. And so I can just do this without the curly braces. Return A. Okay. Here's our recursive call. And remember, we had to put B as the first parameter and then A modulo B as the second parameter. That's it. I'm going to prompt the user again for a number. Oh, I got a little bit carried away here. So I'm going to prompt the user for both numbers. Probably need to prompt the user for what this program actually does. So a silly prompt. Okay. Going to split this into 2 output lines just because of length of line in the code. Okay, then I'm going to put in some error checking. So right here, then I'm going to copy these. So this is okay. Going to dump that into there, and then going to change this to second. But it's the same error message. If I have written my code correctly, this should work. Ooh, I got a bad line of code in there. What line is that? Line 37. It also said line 12. Return Euclid GCD. Okay, next. Line 37. Yeah, I don't know what I was doing there. That was... Oh, and I missed a parentheses. That was my problem there. This is like all about spelling and parentheses and not really anything about the code. There we go. So let's try executing Euclid. So let's check our error checking first. Won't take a negative number. Shouldn't take 0. Got the first number. The second number shouldn't be negative. Got the first number. The second number shouldn't be 0. And now a simple base case. 1, 1. And the greatest common divisor should be 1. And it is. Awesome. There's our base, or our initial case. So let's pick one that's a little easier. 24, 12. And the greatest common divisor here is 6. Oh, no, it's not. It's 12. Never mind. Bad brain. 24, 18. And that's 6. Okay. 24, 15. That should be 3. And it is. And it looks like it's working really well. And now I'm just going to try it with some big numbers. Fat fingered that one. Fat fingered that one. And those are mutually prime. That is, they do not have a greatest common divisor. So let's try that again with the same first number, 2734. And this is in the math of prime numbers. So I'm going to go 90125 instead. And these should have a GCD. Ooh, they don't. Ah, that's actually not that common to have, to be able to add 2 to to the odd number and have it still be mutually prime. So let's try that again. We'll add 2 again. So there's the first number, 90127. That's going to be mutually prime. That looks like it, and it is. So 182734 with 90129. Wow, this is impressive. 182734 and 90131. One 2734. Maybe I'm not as smart as I thought I was. 90133. And that's going to be, that's not going to work. Yep. Okay. Make it easier on myself. 182734. And the second number is 90134. 2. There you go. So it seems to be working correctly. I just got a long string of numbers that, it didn't like. I certainly can go back to these 2 numbers up here and rerun this and put in for the first one, 182735, and then 90125. And those will at least have 5 as their greatest common divisor. And it turns out actually 35 is. So 35 divides both of those evenly. So that's Euclid's GCD. And now we're going to write Fibonacci. And Fibonacci is absolutely horrible. I'm just going to call it Fibo. So set no C indent. Found include. IO stream. Pound include. CSTDLIB. Using name, come on. Too many letter transpositions. Name, oh my God, it's like I've never typed before. Using namespace standard. Int fib, fibo of an integer n. Now Fibonacci has 2 recursive calls to set this up, and it's really a bad algorithm. So if n is equal to 1, whoops. Then we simply return n. Okay. Otherwise, we're going to return. Now, how do we calculate the nth Fibonacci number? Well, we add together the prior 2 Fibonacci numbers. So we're going to make a recursive call to Fibo of n minus 1, and then we're going to add to that a recursive call to Fibo for n minus 2. Okay, so these are that's the prior Fibonacci number, and this is 2 prior. Okay, so we're working this backwards, right? I want the 10th Fibonacci number. Well, I have to have the 9th and the 8th and add them together. If I want the 9th, I'm going to have the 8th and the 7th and add them together. Okay, and that's it. Pretty straightforward. Pretty frickin' awful. I'm just going to say this, and we'll see in a second why. Okay, so I'm going to need the num. I'm going to need to I'm trying to figure out a good way to prompt the user for this. Not the greatest prompt, but it'll work. So we print out our error message, and then we exit. Give it a space, print out the number. Okay, so that's our program. I did spill over on that 70 line thing here, so you can see again, that's a little ugly, but I didn't feel like splitting this one up. Let's compile it and see if it works. G++, dash O fibbo, and then I want to compile fibbo.cpp. Hey, boom, that was fast. Avast has decided that it's okay. I misspelled want. Oops. So let's do some really simple ones. Oh my goodness, I completely forgot my base cases. I better Control C out of this. I didn't completely forget my base cases, but I got some problems here. Don't I? No, actually I don't. Maybe I'm okay. We'll see in a second. So Fibbo. Nth Fibonacci do I want? The third Fibonacci should be easy. That's 1 plus 1. So that's 2. Ooh, ooh. I did not hit the base cases the way I wanted. Okay, so I did have a problem with my base cases. I should have trusted my instincts on that. And that's where my problem is, I do believe. Because remember, the first Fibonacci number is 1, the second Fibonacci number is 1, and you got to have those two correct. And that means I do not want to return n here, I want to return 1. So if the first Fibonacci number is 1, so we return 1. The second Fibonacci number is 1, so we return 1. That makes more sense. So let's see if this one works. Now notice that segmentation fault core dump occurred. That actually means that we recursed so many times that it ran out of memory and it tried to use memory it didn't have allocated. So this seg fault is still a bad memory problem. So let's try 3 again. Oh, it's so bad. What did I do this time? Fibbo the Nung. So I'm going to put in a debug print statement. Oh, I forgot to recompile last time. At least I think I did. I know I did because I didn't get the virus scan. That was my problem. So I really didn't need that print statement, but the print statement will show us how deep the recursion goes. This is ugly. Okay, so calling with 3, calling with 2, calling with 1. The third Fibonacci number is 2. Okay. The fourth Fibonacci number should be 3. It is. Notice the calls piling up. The fourth Fibonacci number should be 5. Okay. Okay. Oh, no, the fourth. The fifth Fibonacci number should be 5. Yep. The sixth Fibonacci number should be 9. No, 9, 8. 8. So the sixth is 8. Look at all of those calls. Now, see, the problem is, and this is subtle, that in order to calculate the Fibonacci of 6, the sixth Fibonacci number, you need the fifth and the fourth. But to get the fifth, you need the fourth and the third, which is down here. So these things recalculate, and they recalculate exponentially. So there's a combinatorial explosion here. So if I go back and edit out that debug statement, okay, where is that? Right there. So I get rid of that, recompile. So we had tried the sixth one. Okay. So the seventh Fibonacci number is 13. I got to wait for my virus scanner. So the seventh Fibonacci number is 13. The eighth Fibonacci number is 21. The ninth Fibonacci number is 34. Let's try the 15th Fibonacci number, 610. How about the 20th Fibonacci number? How about the 30th Fibonacci number? Now this is where the combinatorial explosion should slow down my machine. Ooh, not quite yet. How about the 40th one? You could see that delay in there, right? The 50th Fibonacci number? So at 50, the combinatorial explosion has essentially killed my machine. Now, this one doesn't go infinitely deep, so it's not going to cause a crash of the program. It is, however, going to take an exceptionally long time. Well, you could see, from 20 to 30, no, not much. 30 to 40, just a little bit of a delay. 40 to 50, and it's taking a long time, a really long time. So recursion, really good for things like Euclid's GCD. It's okay for factorial, but it's really horrible for Fibonacci. I mean, really horrible. In fact, I'm going to Control C out of this and try 41 instead. So there's a little bit of a delay. How about 42? A little bit more of a delay. How about 43? See the delays getting longer? 45? Oh, this might overflow the int. Ooh, it didn't. Okay. So you can see how long that's taking. Just adding a couple to it takes a lot longer. And that's what we call combinatorial explosion. It explodes according to a factorial. The combinations of n things taken I at a time involves factorials. And so that is the end of today's lecture. So I'm going to drop the share here, and I'm going to stop the recording, and we'll see you again next week.